So, hello everybody. Thank you for this very kind invitation. So today I would like to talk to you about a specific reconstruction technique, which is the extended fast action minimization method, or eFAM for short, which aims at recovering both the path density field and the velocity field on cosmological scales. So I will skip the introduction of my talk, and I will go directly to give you some insight on the standard reconstruction technique, to then go into the details of eFAM, so the code I have been developing, and then assessing its validity by reconstructing a set of simulated dark matter halo catalog and comparing the reconstructed two-point correlation function with theoretical prediction. Lastly, we conclude by showing you the latest results we have obtained by reconstructing the BAO signal coming from SDSS DR12 using the combined sample. Sorry, I just skip this. Okay, so skipping all this part, we don't need. Okay, so as I think you know, reconstruction was was introduced to alleviate the broadening of the acoustic peak in the two-point correlation function caused by nonlinear displacement of galaxies that occurs from the epoch of the CMB to late time. And moreover, was also included to try to correct for the effect of redshift space distortion, which cause, if you look at the plots on the bottom of this page, cause the breaking of the anisotropy of the anisotropic two-point correlation function. And in particular, on small scales, was producing an enhancement of the clustering along the line of sight here, the y direction, and also on larger scales, an enhancement of the power along the perpendicular direction that's called the Kaiser effect. So the effect of nonlinearities together with the effect of redshift space distortion make the measurement of the BAO scale more difficult because introduce source of error. So the aim of reconstruction is to alleviate both those effects by going backward in time and displacing the galaxy back to the real space position in the linear regime. So the standard Zeldovich reconstruction, it was introduced by Einstein in 2007, simply works by start to providing an estimation of the linear density field, starting from the observed density field. So in practice, what you had to do is to take the distribution of galaxies in co-moving space, and then to apply a smoothing filter, aiming at removing the source of nonlinearities, and then to use this linearized field to compute the Lagrangian displacement. After that, every galaxy was shifted back to the minus the sign of this displacement to obtain their real position. However, this operation of applying a smoothing filter caused us to miss some scales, some power in our power spectrum. So we need to recover it. We need to apply the same displacement to a random field with the same selection function of our data, and then to displace it back in time. Our reconstructed density field will then be defined as the difference between the displaced data and the displaced random field. With this operation, we can recover also the small scales we were missing with because of the smoothing filter. So despite its efficiency in recovering the two-point correlation function, so the linear field on large scales, the Zeldovich technique has some intrinsic limitation. In particular, so it's really limited to large scales. And also the quality of the reconstruction itself depends on the smoothing scales. So if you think that since we know that the broadening of the peak, which is parameterized by the parameter sigma nonlinear, can be seen as a proxy for the time, since moving from CMB, so early time, to late time, what we do is just to broaden this peak. When we actually go back in time, we will expect to be able to recover a smaller sigma nonlinear parameter as, sorry, it's confused. So if you use the proxy of sigma nonlinear as a proxy of time, we can imagine that if we reconstruct our two-point correlation function back in time, we should be able to just shrink the peak, so lower the value of sigma nonlinear. However, I show you this in the plot on the top left. Here you see the effect of reconstruction just changing the smoothing parameter. you see that the curves differs from the value of sigma nonlinear. So in this case, sigma nonlinear is not anymore a proxy of time, but it's just a consequence of the choice of the smoothing scales. And moreover, this choice of the smoothing scales introduce a fake artificial dependence in K, which prevent us to actually recover the linear power spectrum, but we obtain a modified linear power spectrum. So all these features point towards the need for an alternative reconstruction technique, which could be used to extend the scale of range outside the BAO peak and to provide the nonlinear modeling of the density field and Rashid space distortion, and to recover the real past density field, so not the modified version of the 2-point correlation function. For this reason, we implemented a new nonlinear reconstruction technique, which is based on the least action principle. And it aims at recovering the past orbits of the mass tracer by minimizing the action of the system. The code works by applying mixed boundary condition. So we set the observed position either in real space or in the Rashid space of the galaxies, and then we assume that the initial peculiar velocity of the galaxies are vanishing. This assumption corresponds to assume that universe is homogeneous and isotropic at early times. Moreover, our action of the system is described by describing the interaction of collisionless equal mass point-like particles interacting only by gravity in an expanding universe. And since we are only interested in very large scales, we can use the Newtonian approximation. The minimization of the action is carried out by expanding the orbits of each galaxies on a series of orthogonal polynomials and finding the sets of coefficients to define this function that stationarize the action. So, oh, sorry, I moved on the other direction. Okay. So the extended fast action minimization method is a new implementation of the fast action minimization and the least action principle, which is especially designed for application to current and future massive spectroscopic surveys, in particular to deal with order 10 to the 7 objects and working on gigaparsec scales. Moreover, is able to account for the bias of the tracer, the presence of masculine region, and also the survey geometry. It also provides the nonlinear velocity field and the density field from 10 megaparsec to gigaparsec scales, and is not fine-tuned to a specific probe. So different from Zeldovich that is mostly used for example, BAO reconstruction, we can apply the reconstruction on a density field of a survey, for example, and then use the reconstructed density field for analyzing the velocity field, the BAO reconstruction, for example, or also the signal coming from voids. Lately, we are also applying this method to the investigation of the cosmic web. So differently from the fast action minimization, we generalize the algorithm by allowing to consider a variable cosmology, a lambda-Symbian cosmology for the evolution of the background. And to do so, we change the expansion of the polynomials that describe the orbits. And we define the polynomial as the Jacobi polynomials, and we fit the weight of that defines the orthogonality of the polynomials to the evolution of the cosmological parameters. A key point in this discussion is that the choice of the cosmological parameters that we need to put to describe the evolution of the background has a very small impact on the final outcome of the estimation of peculiar velocity. In particular, we estimate it to be below the 6%. When we reconstruct in Rashid space, our action has to be slightly modified because we have to guarantee that if we minimize the action with respect to the coefficient and not with respect to the wall trajectories, we obtain the equation of motion. And for this, since we need to impose that our boundary conditions are Rashid rather than position, we need to add this additional term. Okay, so this is the theoretical framework of the code. And to assess its validity, we decided to apply to the reconstruction of 512 subcubes extracted from the Del-Spur embodied dark matter halo catalog. So to ensure the statistical independence of the subsample, so I will call mock, we took the full 21 gigaparsec box and divided it into 500 subcubes separated by a buffer region of 500 megaparsec. At this scale, the 2-point correlation function goes to 0, so we can consider the boxes as correlated. We then have computed the 2-point correlation function before reconstruction, using the Landin-Saleh estimator. And then after reconstruction, up the observed redshift, so only after having computing the velocity field and removed every redshift by distortion. And then we went also backwards in time to try to recover what is the linear two-point correction function. So here you see the results of the reconstruction of the simulated catalog when applied in real space. So in this first stage, there are no redshift by distortion. Here we can see that in blue, there is the two-point on the left, the two-point correction function before reconstruction, and is compared to the linear prediction, which is indicated in black. What is striking is that, as expected, the BAO signal is damped. And this is also visible when looking at the sigma nonlinear parameter, that is, his value is 11.8, and it was supposed to be 0 for the linear theory. So we then went backward in time to different redshift. You see an intermediate redshift in green and then a higher redshift in red. And you see that we can progressively approach the linear theory and progressively shrinking the sigma nonlinear parameter. So this is again underlines the first difference with Zeldovich. So we can actually use the sigma nonlinear as a proxy of time. And I also want to stress here that we didn't have to use any smoothing scales. On the right, I compared the results of eFAM with the results of Zeldovich-like reconstruction. So what we have done is just that in our minimization, we have imposed our trajectory to be straight lines and to have constant velocity. So the results here are plotted at the same redshift of the reconstruction for the full eFAM. And what you see that is in the intermediate redshift, we approach the linear theory, but not completely. And going to a higher redshift, we see that we start to deviate and bias our results from the linear theory. This is a consequence of the overestimation of velocity. So when we overestimate the velocities, what we notice is that we encounter a maximum redshift, after which our signal in the two-point correction function starts to be degraded. So we cannot consider anymore our field to be trustable. So the reconstruction defines what is a maximum redshift here. I would like to notice that the maximum redshift is relatively low, but it's because also in eFAM, we had a very strong overestimation of the velocities that was corrected in later works. So after having computing the mean correction function of all the samples, we also looked at the correction function estimated from single realization. An important feature we discovered is that eFAM was particularly efficient also in recovering the BAO signal in what we call the anomalous sample. So we can have two types of anomalous sample. The first type are the peak for which the BAO signals appears on a Brown scale, so is shifted with respect to the expected position. Here, the shift is represented by a value of the alpha parameter, the difference from unity. So on the top row, you can see on the left, in the blue line, the pre-reconstructed BAO signal is clearly, we have alpha parameter is 1.19, so it's clearly biased. And what we see that after applying reconstruction in the central column, we see that the bias in the alpha parameter is strongly reduced. And if you look also at the chi-square distribution, we see that the minimum chi-squares is sharper and also closer to unity. The second types of anomalous MOCs are the MOCs that don't show any BAO signal. So on the bottom left, you see that there is no clear BAO feature, while after reconstruction, you see that the BAO peak appears and appears close to the expected position. This is even more visible looking at the chi-square distribution, and you see that before reconstruction, the minimum chi-square distribution was showing either no peak or a bimodal distribution, and after reconstruction, we had a single peak centered at the expected position. So those were the results in real space. So after assessing the capability of eFAM and reconstructed the linear two-point correction function, we decide to apply it to the redshift space. So here I wanted to show you what are the results of the reconstruction on the anisotropic two-point correction function. Before reconstruction on the left, you see there is a clear broadening of the peak. And there is the effect due also to the effect of nonlinear RSDs. And there is also a squashing of the BAO ring due to the Kaiser effect. So we can see that the measurement of the BAO ring is made difficult by all those effects. After reconstruction, we can firstly remove, as we did before, the Rashi space distortion. And what we see that we were able to reduce the broadening due to nonlinear effect on small scales, and also to almost erase the squashing due to Kaiser effect. However, we still have the damping of the BAO feature due to nonlinear evolution, since we didn't went yet backwards in time. What is important to notice here that we still have an enhancement on very small scales, but it is because those are very nonlinear scales that we are not able to recover. Post-reconstruction, so going at high redshift, we see that we have no broadening anymore. The ring is very sharper, there is no squashing, and the BAO ring is clearly visible. So we can now look at the mean, monopole, and quadrupole of the two-point correlation function obtained by different realization. And what we see is that already when going from the reconstruction, the pre-reconstructed two-point correlation function in blue to the reconstructed two-point correlation function at the observed redshift, so only without redshift space distortion, we see a small effect in the monopole, which is just the effect of removing the Kaiser distortion, while we see a strong effect in the quadrupole. So the quadrupole underlines the anisotropy of the correlation function, and before reconstruction was clearly not compatible with zero, as we'll have expected for isotropical feature, while after removing RSDs, we have that the quadrupole is compatible from 40 megaparsec to larger scales. Then we also went backwards in time at higher redshift, and we see that we were able to closely approaching the linear correlation function here in black, and the quadrupole was still compatible with zero. So one of the reasons why we were not able to actually reach the linear theory prediction is also because we had an extra source of error in our redshift position that we use for our pre-constructed catalog. And this is because we didn't have the velocity of galaxies to actually construct the exact redshift space, but we had to use the velocity we reconstructed in the previous application, so the reconstruction in real space. However, we can state that eFAM efficiently restored the isotropy and sharps the peak. And this is also confirmed by the results on both alpha parameter and the sigma nonlinear parameter. So those were the results on simulation, and now we were ready to move to the application to real spectroscopic surveys. So when we want to deal with surveys, we also need to account for the specific effect of surveys. They are not present in the simulated catalog. In particular, we need to account for the galaxy bias and for geometry of the survey. So to understand what happens if our geometry of the survey is not spherical, for example, we can just imagine to fill our survey volume with a uniform distribution of galaxies and then compute the gravitational acceleration and potential. So here on the bottom, I show you what is the gravitational acceleration computed by filling the SDSS volume with the uniform distribution of galaxies, and you see that is clearly not uniform, but is present an artificial large-scale bulk flow. But we know from Newton's shell theorem that if we have this uniform distribution of matter, that it's infinite extended all over the universe, we should have vanishing acceleration. So we can treat as the external matter distribution that we don't know as to be also homogeneously distributed, and then compute the missing component of the external tidal field, just as the component that is needed to have a constant potential in our simulated field. So in practice, to do so, we then fill, again, the survey volume with the uniform distribution of matter. We set the total potential to 0. We know loss of generality. And then we estimated the external potential, just the minus the potential felt by the uniform matter distribution within the survey. Then when we were constructed the dynamics of our observed galaxies, we were computing the potential of the galaxies due to the distribution within the survey, and then adding this external distribution contributed with the random field. This procedure is equivalent to embed the survey in an infinite extended random field, but is much more computational efficient because it doesn't require to compute the particle-to-particle interaction for each object. So to see the effect of this correction, I performed the reconstruction on uniform matter distribution without including the effect of external field. And what you see, as again on the left, the results of the velocity field. Again, it presents this effect of the strong bulk flow. While after introducing the correction, we see that the velocities are so much smaller and also randomly oriented. So if you want to see this in a more quantitative way, we can also look at the PDF of the velocity distribution. And we see that pre-reconstruction in blue on the bottom panels, we see that we have a big dispersion of velocity of about 2,000 kilometers a second. And after reconstruction, we can have actually a distribution that it's below the 10 kilometers per second. So we can see that this correction is very efficient of removing this bulk flow. However, it cannot account for the bulk flow due to the cluster distribution that we don't see outside our survey. This is another, say, way of seeing the value of the correction. So instead of using a random field, we actually use the observed distribution of matter. And again, before reconstruction, you can see in the top central panel, you have the effect of this bulk flow. And then if you compare point to point the n-body velocities, so the simulated velocities with the reconstructed eFAM velocities, we see that we have no correlation. So we cannot say that we had a good reconstruction of the velocity field. While after correction, on the bottom right panel, we can see that the correlation is fully restored. So again, we can confirm that this is a good way of correcting for the effect of bulk flow. So the second effect, as I mentioned earlier, is the bias of the matter. So if you want to accurately reconstruct the dynamics of the observed density field, we need to accurately also model the potential that generates the dynamics. So we need to account for all the matter that we have in our survey, both visible matter and dark matter. So to model our total matter distribution, we decided to assume the matter distribution to be my model. So it's composed as a smooth component, a field component distributed all over the survey, the volume of the survey, and a cluster component located at the position of the observed galaxies. In this way, we accounted for the smooth component as an external tidal field, and additionally to the one that we had to account for the bulk flow. And we correct the weight for each galaxies in order to obtain the correct density contrast. So after all this correction, we were able to analyze the SDSS, both the mocks of the combined sample and the data. And in particular, we used the mocks to, again, assess the validity of our new version of the algorithm accounting for this specific effect, and also to be able to compute the correlation matrix needed to fit the two-point correlation function. Here, I show you the results of the anisotropic correlation function before reconstruction on the left and post-reconstruction on the right. You see, as before, that we were able to restore the isotropy of the BAO feature, and in particular to erase the Kaiser distortion. So, but let's see how we can do this quantitatively. So to break the degeneracy between the Hubble parameter and the angular diameter distance, we decided to isolate the information of the clustering along the line of sight and perpendicular to the line of sight, and we did so by measuring the clustering wedges. Then the difference between the fiducial value of our cosmological parameters and the true values is going to be parameterized by the alpha parallel and alpha perpendicular parameter. So with this, we start looking at the pre-reconstruction two-point correlation function. And here, what you see on the left are the clustering wedges, the perpendicular wedge in blue and the parallel wedge in red. And you see that as the first effect, we can see the effect of Rashid space distortion, which manifests itself as a difference in the wedge amplitude, and looking at the monopole in a non-vanishing quadrupole. So again, this is the effect of the anisotropy. So if you want to model the wedges pre-reconstruction, we need to account for Rashid space distortion and for the effect of nonlinearity, so the broadening of the BAO peak. To do so, we used the standard model. So we defined the real space power spectrum as the linear power spectrum with the no wiggle damping regulating by the damping parameter along and parallel to the line of sight, those sigma parameters. And then we have the redshift space distortion as the sum of a Kaiser term, the product of a Kaiser term and a Lorentzian streaming parameterizing the finger of God on small scales. Here, the Kaiser term is regulating by the F over B parameter, while the Lorentzian streaming is regulated by the sigma S, which is the RMS velocities on small scales. From that, we computed the multiples and then of the correlation function of our 2-point correlation function. To then be able to model further sources of noises, we add a broadband term, which is composed by 3 times 2, the 2-direction shape parameters. So in total, we had 13 parameters in redshift space. So we fit the 2-point correlation function in the fitting range 150 megaparsec, which is the standard fitting range also for Zeldovich reconstruction. And what we see is that we have bias scale measurements for both alpha parallel and alpha perpendicular, which is most striking on alpha parallel, and a poor constraint on sigma parallel. Moreover, if we look at the correlation matrix of the fitting parameters, we see that there is a clear degeneracy between the RSD's parameter and the shape parameters. This is because our model is not efficient in actually capture all the sources of both nonlinearities and RSDs present and in our pre-reconstruction data. So if we look at we fit the single MOX of the SDSS and we estimate for each MOX alpha parallel and alpha perpendicular. What we obtain here is the plot on the bottom right, which is the distribution of the dilation parameters obtained by single MOX. And what we see is that we have, again, a poor constraint on sigma parallel. We have a clear, a large dispersion in the value of sigma parallel obtained by single MOX, and also that alpha parallel is biased with respect to the expected value for the known cosmology of the MOX. So for those regions, we need a solution. Either we include a more accurate model for our nonlinearities, either we try to model them using reconstruction, and this is what we have done. So here, to check the consistency of the methods, as we did before, we didn't go straight backwards in time. Well, we stopped to observe a redshift and just to see the effect of removing redshift space distortion. Here are the wedges and multiples of the average 2-point correlation function for the 400 MOX. And you see on the left that now the wedges are almost completely superimposed, showing that the redshift space distortion, at least on large scales, are reduced, and also the quadruples is almost vanishing off on all scales. So we then proceed again on fitting the mean wedges for the correlation function. And what we see that the constraint on sigma parallel is strongly improved. And this because also the degeneracy between the fitting parameters is strongly reduced. This is because we don't have anymore all the sources of nonlinearity that were not well modeled by our template that cause this degenerate. So also, we have one of the more important things we found fitting the 2-point correlation function at the observed redshift, that now both the parameters that describe redshift space distortion, linear f and nonlinear sigma f, are compatible with 0. So we are allowed to decrease the number of free parameters from 13 to 11 by removing the part of the template that was accounting for the effect of redshift space distortion. So we then used this real space template to fit the reconstructed 2-point correlation function at higher redshift. Just to check the consistency, we can see now that the peak is sharper. So this also indicates that we were also able to recover part of the nonlinear evolution of the galaxies, and the wedges are still superimposed, and the quadruple is still compatible with 0. What we see on large scales here, so a bit noise and deviation from 0, is the effect of the edges of the surface in which the reconstruction starts to degrade. In the future, when we can have like larger volume, we were able to cut bigger buffer regions around the survey edges and then try to alleviate those border effects. So here are the results of the fitting of the mean of the wedges again. And you see that the constraint on alpha parallel and alpha perpendicular are improved with respect to both the pre-reconstruction and the reconstruction at z equal observable ratio, sorry. And this again indicates the fact that we removed nonlinearities that were not accurately modeled by our template. We had a lower value of both the damping parameter, proving that we went efficiently backward in time. Again, we have no degeneracy within parameter, and there's this parameter still compatible with 0. So we can check that we made a good choice using the ratio space template. Here there is the comparison of the results obtained by fitting single MOCs for the pre-reconstruction and the post-reconstruction at high redshift. And you see that reconstruction allow us to reduce the bias of the alpha parallel and alpha perpendicular, giving us a mean value for those parameters which is compatible to 1, so with expected cosmology. And moreover, we also have a reduction of the uncertainties on the parameters. So strong of those results, no, sorry, that isn't another thing. So those were the results of our fitting of the template in our fiducial range, so 50 to 150. But another thing we want to show is that since we correct nonlinearities, we can safely reduce the value of the minimum boundaries of our fitting range and trying to capture more linear scales. So what we discover here is that if we enlarge our fitting range from 50 to 150 to 25 to 150 megaparsec, we see that before reconstruction, if we look at the value of the alpha parameters and his uncertainty, we see that the pre-reconstruction, the bias starts to increase, again, demonstrating the fact that our template, fiducial template, is not able to capture nonlinearities that become stronger at smaller scales, while on the contrary, post-reconstruction, we find that our estimation of the alpha parallel is stable under those changes. And moreover, we don't see a clear increase in his uncertainty. So we can conclude that we can safely extend the fitting range and perhaps starting to think about a full shape analysis post-reconstruction. So those were the results for the MOCs. And with those MOCs, we were also able to compute the covariance matrix both before and after reconstruction. So what we have done, we have computed the wedges and the wedges of pre and post reconstruction for our SDS data, and we have fitted our wedges with both a template accounting for the nonlinearities and including the BAO signal, and a template we was not including the BAO signal. With this, comparing those two templates, we were able also to determine what is the significance of the BAO detection. And what we found is that before the construction, the significance was only 2.1 sigma, while after reconstruction, the significance was higher and of about 4.54 sigma. So, and again, in concordance with what we saw in the MOCs, what we can detect here is that the signal, the RSD signal that was clearly visible in the pre-reconstruction wedges is not anymore detectable in the post-reconstruction. The peak is sharper, and again, the significance is way higher. So we then showed the results of the fitting of our wedges, and here, instead of directly focusing on the alpha parameters, we convert them into estimation of the Hubble parameter and the angular diameter distance. And what we saw is that the uncertainties of the Hubble parameters is reduced from 3.5% to 2.2%, and one of the on the angular diameter distance is reduced from 5 to 3.6%. And more importantly, the post-reconstruction, we have a better agreement with both the fiducial cosmology and the results obtained by Ross et al. 2017, in which they were reconstructing the two-point correlation function of the same dataset. So this concludes what is the analysis of our two-point correlation function. And just before finishing, I want to show you the results on the first preliminary results on the analysis of the cosmic voids. So we said at the beginning that our reconstruction technique is not fine-tuned for any specific probe. So we use the same reconstructed density field that we use for the BAO analysis to actually trying to measure the void statistics. So here, only focusing on the effect of ratio space distortion, we have computed the pre-reconstruction cross-correlation function of the voids for 10 MOCs of the SDS-SDR12 realization. And what we see is that the cross-correlation is not isotropic and is characterized by those two banana-shaped features along the line of sight. So here I want to stress that we use the same cosmology of the MOCs. So we are not expecting to have any distortion due to the Alco-Paczynski effect, so the effect of having assumed the wrong cosmology, but the distortion we have, those are only due to the effect of ratio space distortion. So this is important because if we want to use the distortion to measure our cosmological parameters, we can see that we can actually increase the uncertainty on the cosmological parameters because there is a strong degeneracy between RSDs and Alco-Paczynski. So what we have done, we have used the reconstructed density field at the observed redshift, so only after having removed ratio space distortion, and we have computed the cross-correlation function. You see the results on the right panel, and you see that here there is no anymore the presence of those two banana shapes. So, and the isotropy is almost fully restored. So we can say that we can use reconstruction to break the degeneracy between RSDs and Alco-Paczynski. More importantly, here we were able to use also only 10 MOCs and see this clear feature in the cross correlation, because being nonlinear, we were able to use voids as small as 15 megaparsec of radius, as opposed as the 40 megaparsec used to Zeldovich, since we were able to also correct for very small ratio space distortion. So that's the future application we are now investigating in collaboration with Maria Hubert, Alice Pisani, Adam Oken, Enzo Franchini, and Giulia Degni. And this will conclude the my talk on the reconstruction. So I leave you with the summary. And so we had shown today that eFAM is a fully nonlinear reconstruction technique, which is specifically designed for application to massive spectroscopic survey. And when applied to simulated halo catalog, is able to recover the linear two-point correlation function in both real and ratio space. And that its application to SDS-SDR12 MOCs and data show that eFAM can efficiently model RSDs down to 30 megaparsec scale, allowing us to reduce the number of free parameters from 13 to 11. It also allows us to increase the significance of the detection from 2.1 to 4.4 sigma, and to reduce both the bias and the uncertainty on the estimation of both H and the angular diameter distance. Its preliminary application to cosmic voids shows that eFAM is able to break the degeneracy between RSDs and Alco-Paczynski. And thank you for the attention.